All right, we're talking about catalysts, or the subject of catalysis. Let's start with definitions. A catalyst is a substance that increases the rate of a reaction without itself being used up. Right? So it's important to remember that it's not a reactant. All right? There are two types of catalysts. Catalysts that are in the same phase as the reactants, those are called homogeneous catalysts. Okay, so like aqueous, if your reactants are aqueous, your catalyst is aqueous, you have what's called a homogeneous catalyst because it's in the same phase. Solid, liquid, gas, aqueous, okay? And the other type of catalyst is if it's in a different phase, that's what we call a heterogeneous catalyst. So if the reactant was a gas, but the catalyst was a solid, for example. All right, so whenever the catalyst is in a different phase, it's a heterogeneous catalyst. If the catalyst is in the same phase as reactants, it's a homogeneous catalyst. Okay, so let's talk about heterogeneous catalysts first. So in this example here, our reactants are gas, and our catalyst is solid. All right, so the catalyst in use is platinum. So a lot of times when gas molecules react, you guys understand, we went through collision theory, and you know that the important factors are energy and orientation. Right? Getting molecules to collide at the proper angles, just moving around in free space, is difficult, and it's not very efficient. So the platinum or solid catalyst provides an area for reactants to congregate. And see how the reactants here, if we've got carbon monoxide, nitrogen monoxide, they end up congregating on the surface of the platinum catalyst. So here they are, all hanging out. And so when you have molecules that stick to something, that's called adsorption, when they stick to a surface. Not absorption. Absorption is when molecules pull themselves within another substance, like a paper towel absorbs water, right? Adsorb just means they stick to the outside of it. Okay? So anyways, you have this congregation and clumping of reactants. Now, when they attach to the surface of the platinum, they might react on the spot, right? Or it's more likely that because they are now collected in one area, you have more collisions with a molecule that is stationary. And that makes for more effective orientations and higher rates of reactions. Is because they're kind of stood up against the wall and they're flattened there, and that makes for easy collisions. All right, the angle, the fact that they're stuck to it increases the angle of orientation. And then once the products, so these are the products that are formed, and then they leave. They desorb. Think of the platinum catalyst here as kind of like a singles bar. All right, so you go to a singles bar, there's lots of people already concentrated in one spot, and hey, you might leave with a date, right? Who knows, right? So you enter alone, you react, you leave, now you're something else. All right, maybe that's a bad example. So in general, this is how heterogeneous catalysts work. And solid catalysts are typically platinum, typically metals. Metals are the solid catalysts in most cases. All right, so let's talk about the second type, which is a homogeneous phase catalyst. So gas plus gas or aqueous plus aqueous, right? Those are the most common scenarios. I guess you could have liquid with liquid as well. So if we look at this energy diagram, our reactant, and let's color code this to make this easier to see. We'll make reactant 1 this orangey color. Oops, sorry, that's the wrong one. Who's this guy? Okay, we'll make the other reactant red. And we'll make the catalyst green. All right. So reactant 1 is going to react with reactant 2. Now, on an energy profile, this line right here, we talked about this last time, is the difference in energy between the transition state, which is the peak of the hill, and your energy state of your reactants. This is the activation energy, or the energy of activation, the EA value. If this y-axis were numbered, we would be able to get a value for this. All right, so, but notice that when a catalyst is involved, notice how small the activation energy is. That represents the catalyzed activation energy, significantly lower than the uncatalyzed. So, what's happening? How does that happen? Well, we have a collision where R1 binds with the catalyst right here, and then R2, the reactant, second reactant, latches onto the catalyst, and then as the migration of R2 on the catalyst occurs, once they come into contact, once R2 comes into contact with R1, the catalyst is released. And so this process requires very little energy in comparison. Now you might notice that this happens in sequence, and so this would then indicate a two-step mechanism. The catalyzed pathway is a two-step because this point right here, this is an intermediate. And so is this. We have two intermediates compared to the original blue line, which is uncatalyzed. In the blue line, there's no intermediate. It's a one-step mechanism, which means, the angle has to be right, orientation, all that. Energy has to be right. Takeaways. Catalyst is unchanged from the beginning. It enters and exits the same. Okay, now that's not to say that all catalyzed pathways have multi-steps. This is in this particular example it is, right? But the bottom line, the main point, is that your catalyst lowers the activation energy. Your catalyst enters and exits the same way. That's the main points. However many steps there are is a different discussion. Okay, so do you guys know the difference? Well, first of all, can you define a catalyst? And do you know the difference between homogeneous and heterogeneous? And can you describe how each one of them works? All right, so The heterogeneous, you're talking about a solid phase typically, and that allows the space to congregate, for the reactants to congregate and react. Homogeneous, there's no single surface for any place to catalyze. It's just that the molecule binds with the catalyst wherever it is, and that makes for easier reaction. Okay. So here's an example. Hydrogen peroxide decomposes. Hydrogen, we use iodide as a catalyst to decompose hydrogen peroxide. And that's right here. Here's the iodide. So in this mechanism here, using the catalyst, if we algebraically add these two together, you should notice that I minus, the catalyst, gets canceled. And during this, there is the production of this formula right here. That's called hypoiodate, IO minus. It is the product of the first mechanism step, and it is a reactant in the second mechanism step, and algebraically it is eliminated. Right? So this is the definition of an intermediate. Intermediates do not appear in the overall equation. Because they are canceled. All right. So, be able to identify both the catalyst and an intermediate in a reaction mechanism, right? However many steps there are. All right. Let's talk about activation energy. So, if you think about it, if you had a gallon of gasoline sitting in your garage, gasoline is highly combustible. Wouldn't that be dangerous to have gas just lying around your garage? Is it a big deal? Are there warnings saying do not store this in your garage on a container of gas when you buy it? No. Why is it generally considered okay to have a gallon or two of gasoline sitting around in your garage? Won't it go off any second and explode, blow up your garage? It will not. And the reason why it will not is because it takes a significant amount of energy to get that combustion reaction started. That amount of energy to get the reaction started is the activation energy. So if we plotted, here's the energy profile for the combustion reaction, right? You would need a match, a spark, to get that to occur. Yes, we know it's going to release a lot of energy. Yes, we know it is very, very exothermic, right? It's negative. Okay, so we need to be able to, we need to run a couple experiments so we can determine what activation energy is, what the value of it is. So first, this is known as the Arrhenius equation. All right, there's a mathematical relationship between energy of activation, EA. Right, activation energy. It's said both ways, but the symbol is E sub A. Okay, there's a mathematical relationship between it. There always seems to be mathematical relationships between energy and reactions. And so, if we look at the Arrhenius equation, it involves what's called a frequency factor, which is a variable we have not seen before. And that's multiplied by E raised to the negative EA over RT. Okay. So the thing about the frequency factor is that this is always changing, or I should say it's reaction dependent. And it's kind of cumbersome to use this equation in this form. So rather than try to come up with the variables and try to find the value of A each time for every reaction, which is a temperature-sensitive reaction, let's take the natural log. By taking the natural log, we arrive at this equation, which is rearranged into y-intercept form, right? It's a linear plot. What you're seeing here is a linear plot where the x, we're plotting the inverse temperature on the x-axis, Kelvin, inverse Kelvin, of course. And we're taking the natural log of the rate constant here as the y, and our slope is the opposite of EA over R. Now, remember that we are talking about energies now, right? So R is not the gas constant 0.0821. R is 8.31 joules per mole Kelvin. Or, if we want to cut to the chase, because energies are typically, on a per mole basis, are typically expressed in kilojoules, 0.00831 kilojoules per mole Kelvin. Either which way, it's on your formula sheet. Okay, so how do we use this then? How do we determine what the activation energy is? Well, essentially, you need to find the slope, because if you can find the slope and R is known, that's how you're going to arrive at the activation energy. Now, we have a few. In order to find this, we need to run this at different temperatures, because after all, our y-axis, we're plotting the inverse of Kelvin temperature, which means we need to run trials at different temperatures. So if we were to take the natural log equation and if I run a reaction under two different temperatures, we'll call this first one here, we'll write a second one in red. Whereas the red one is, let's say that was our first trial, so I'm going to give it subscripts here, K1, T1. Whereas the blue was our second temperature, K2, T2. By taking a ratio, right, if I take the quotient of these, that's going to allow us to cancel the Arrhenius constant, or the frequency factor. And that's good, because that's a pain to have to find each time. So now we can solve for the activation energy independent of having the frequency factor, which I don't have enough of those to provide you anyways. So it's a good way we're going about it this way. And so the result then becomes this. If we take the natural log of the ratio of K2 over K1, that is set equal to the negative EA over R, and we're multiplying it by 1 over T2 minus 1 over T1. And it's this form that we will use graphically to allow us to find the slope and then determine what the activation energy is. And this is what our lab is on tomorrow, actually. So we are going to take a reaction, and we're going to determine the rate constant for the reaction graphically, and then we're going to take the temperatures of them, of course. And then once we have the different rate constants and different temperatures, that's going to allow us to plot a value to come up with the slope, and the slope is going to give us the EA. So, all right. So let's try some examples. Get your calculator out. All right, so suppose the rate doubles when the temperature increases from 25 to 35. Remember, this is a loose rule that we applied earlier in an earlier lab, the iodination lab maybe, where we increased the temperature or we lowered the temperature from 20 to 10, or you calculated the rate constant, and you saw that the rate constant was approximately half when the temperature was decreased by 10 degrees, right? So let's let's use that notion here, and let's solve for the activation energy. So because the rate doubles when the temperature increases, let's assign some numbers here. We'll call 25 degrees T1, we'll call 35 degrees T2, and that means K, which is not told to us, at least not explicitly, we're going to use K2 and K1, but you're just literally going to use the numbers 2 and 1. The units here are arbitrary because the unit ends up canceling out. So what we have, and remember that this must be in Kelvin, so this is really 298, this is really 308. So our setup, the natural log of K2 over K1 is equal to negative EA, which we're solving for, and over R. Now R, 0.00831 kilojoules per mole Kelvin, multiplied by 1 over 308 minus 1 over 298. All right. Let's see what we come up with. Now your negatives should cancel here. And then what you should end up with, if you did the same way I did, is about 52.9 kilojoules per mole. We get that okay? All right, I worked from the left side first. I took the natural log of 2 first, and then I divided both sides by the temperature differential in parentheses, and then I multiplied by 0.00831, and then the negative canceled, and that's how I got that. Okay, let's try another one. So here it says, suppose that the rate constant here is given at 0 degrees, and the activation energy is given, that's per mole, that's kilojoules per mole. Find what K2 is at 100 degrees. Now, of course, you have to convert to Kelvin, so really what you're dealing with is 273 Kelvin here and 373 Kelvin here. All right, but you're solving for K2 this time. So the value for this is going to seem pretty large, but consider what we're doing. We're taking something from 0 degrees and increasing it by 100 degrees, right? So it's not just doubling, you're doubling it 10 times, right? So K2, what do we get? And the unit is in 1/seconds. What'd you get, Zoe? Yeah. It's a big value. A little unwieldy, but that's how we would do it based on the equation we have. Okay. All right, so activation energy, rate constants, temperatures are all related. You can solve for one or the other using the equation, but you can also solve for the activation energy graphically, which is what we're going to do tomorrow. All right. We are not going to... Well, actually, no. Yeah, we should. We could do this real quick. Okay. So, before we move on, are you guys questions on activation energy? So, in a problem like this, in any kind of instance where you need to find the activation energy, you're going to need rate constants, right? The rate constants will either be provided to you in a problem, or if it's a long problem, you might need to come up with the rate constant yourself. So, speaking of which, let's back up a second. Let me insert a page here because it's been a while since we did that. Remember that to find the rate constant, there's lots of ways. But what you're looking for is the linear plot, the ln of the concentration versus time. M is equal to the opposite of the slope is equal to the rate constant. So let's say you're starting with raw data, all right, and you just have concentrations versus time. You need to plot it, and you need to figure out that what the rate constant is, which means you need to find the linear plot. Now, this is for first order, right? Remember that if it's second order, you're plotting the inverse of the concentration versus time. And that means M is equal to K. That's how you find the rate constant if it is second order. And then remember that if it is 0 order, if it's 0 order, the rate constant is the opposite of the slope, and it's actually the rate is the rate constant if it's 0 order. So if a problem involves activation energy, but it doesn't seem like they gave you rate constants, what that's indirectly telling you is that you need to find the rate constant first. And then you need to use the derived Arrhenius equation to find the activation energy. Okay? All right. So let's talk about radioactive decay real quick. This is a more extensive unit. Sophomore year, we don't really cover this too much. But when we're talking about radioactive decay, the basic idea is this. The nucleus of an atom may or may not be stable. So if it's unstable, the nucleus is going to undergo radioactive decay. There will be some kind of particle emitted. And then because the particle emitted changes the complexion of the nucleus, you get a new element. All right, and these particles are things, you might recall them as alpha particles or beta particles. All right, right now, we're not going to focus too much on that because that's not actually within the scope of this course. But what you should know is that radioactive decay is always first order. And that's helpful to know because that gives us flexibility and it kind of sets us in the right path on how to solve these problems. So, because it's a first order process, your rate law for nuclear decay is essentially rate is equal to K times N. Now, N is the number of atoms. It's not a concentration, right, like it is for a reaction. Okay? It's just the number of atoms. And the rate is expressed as atoms disintegrating per unit time. And that unit time is typically seconds. There is a basic or a common unit, and that unit is what we call a Curie, named after Marie Curie, right? And so a Curie is 3.7 times 10 to the 10th atoms disintegrating per second. This is not a value you need to memorize, right? Think of it as a conversion factor, okay? So let's say that for radium, the rate constant is known. When we say calculate the activity, we want to find how much, what the current rate is. So, a couple of things we need to do to solve this. First, 1 milligram sample, our rate is expressed in atoms disintegrating per second. So we need to convert milligrams into atoms. So 1 milligram, there's 1,000 milligrams per gram. And on a mole of radium, this isotope here, radium-226, weighs 226 grams. And in a mole, you have Avogadro's number, atoms. Okay, so we got to figure out how many atoms there are present in 1 milligram. We crunch the numbers, 2.66 times 10 to the 18th atoms of radium-226. Okay? So, since it's the rate that is being asked for, the activity, when they say activity, they mean rate. So the rate is the K times N, and the rate constant was given to us. 1.37 times 10 to the negative 11th atoms per second. That's not very clear. Let me rewrite that. Times the number of atoms. I'm sorry, the rate constant did not have the term atoms in it. So after calculating, then we get our rate of 3.65 times 10 to the 7th atoms per second. And that is the activity based on the amount that you have. Okay, so the key to solving that problem was understanding that the activity is atoms per second. Atoms per second. Okay. Let's try another problem. So the half-life of uranium-238 is 4.5 times 10 to the 9th years. How long does it take for 60% of a sample to decay? All right, so remember how we said that decay is always first order? So if they're asking for how long, they're asking for time. And they're indirectly giving us amounts. They say 60% is going to decay. So what does that mean? What is my original amount if 60% is decaying? Because they didn't give me a hard number. They didn't give me an actual mass measurement or anything. So what value do I use as my original amount? Ron? 1 or 100%. Okay, so that means amount initial is equal to 100%, and amount final, or A sub t, if 60% is how much is lost, that means we are left with 40%. Yikes. Okay, so interesting. Where have we seen these symbols before? A sub naught, A sub t. Where do we see these? What are these from? Yeah, it's from our integrated rate law. Okay, so if they're asking us to solve for time. But here's the thing. In order to solve for time, let's play around with this equation first. We don't have the k. We don't have the rate constant, so we have to find the rate constant first because it wasn't given. And this is a common thing that you're going to have to do. So, what do we know? How would the rate constant be solved for generically? Well, since half-life is what is cited, the ln for half-life would look like this. You guys understand? A sub naught is the original. A sub t is the final. The definition of half-life is how long it takes for half of your sample to decay. So my original amount, if it's 1, my new amount is 0.5, because that would represent half of the sample going away. T is the time, but if we're specifically talking about cutting this amount in half, then t is the half-life. So that means the ln, well, 1 over 0.5 is 2, of course, right? So it's the ln of 2. I'm going to divide both sides by k, and that's going to be set equal to the half-life. So this is the half-life equation for a first-order reaction. Ln of 2 is 0.693, so 0.693 over the half-life is how we find the rate constant for the first-order decay. And the half-life was given here. So we can find k. So 0.693 over 4.5 times 10 to the 9th years is equal to the rate constant. Which means k is equal to 1.54 times 10 to the minus 10th, 1 over years. And now I can actually solve the problem, because now I have what is needed, and what was needed was the k. So now we do the problem again, but this time we use k and we solve for time. So again, the initial amount is 100%. The new amount is 40%. And we're gonna divide it by k, which is 1.54 times 10 to the negative 10th years to the minus 1 is equal to the half-life. Or sorry, no, not the half-life, the time. Time, not half-life, just time. Okay. And it's going to be a while. Was that 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. About 6 billion years. No big deal. I'll go get a cup of coffee. Go to the bathroom. Come back. Okay. Last problem. Try it on your own. See what you get. Begin this problem the same way that we began the last problem, meaning you need to find what the value of the rate constant is first. Once you have the value of the rate constant, that's going to allow you to find the half-life. And then once you have the half-life, that's going to allow you to answer the second part of the question. Okay, so if you're not quite done, that's okay. So ln a sub naught over a sub t is equal to kt. So to find the rate constants, we have our original and our final amount, and that's what we had after 2 years. So the rate constant can be found by setting that up. And after doing that, Did you get rate constant to be 0.0241? Okay, so that's our rate constant. So to answer the question, what's the half-life? The half-life is the ln of 2 over k. So ln of Q2 is 0.693 over 0.0241. And so we end up with about, 28.9 years for the half-life. Okay. And then, how much do you have after 5 years have passed? So now that you have the rate constant, and you have the time it takes, you can solve for the new amount. So ln of the initial amount, so if our initial amount was 1 gram, the new amount is what you're solving for. So 0.0241 and time is 5 years. What did he end up getting? What's our final amount? 0.88 grams, right? Okay, which, you know, I mean, think about it. If the half-life is 30 years, if you only let this age for 5 years, it's not going to be cut in half. It's only going to decrease by a little, so that should make sense. All right. Fun with half-lives.